Okay, welcome. And this is a presentation on doing authentic learning in math by doing computer coding. I'm going to tell you a little bit about my background in history and how it led me toward bringing computer coding into the math classroom, walk you through some of the tools that I've used, and we're going to spend a little bit more time looking at my favorite tool, which is JavaScript and Khan Academy. And then also talk about some different styles of setting up lessons and projects using coding in math class. We've done quite a lot of it this year. This is sort of in an experimental mode for me, but I'm looking forward to the dialogue. So let's get started with the presentation. I did start the recording. These are some of our sponsors. Want to thank them for helping make this conference possible. We'll go ahead and do the math activity. So let me turn on the whiteboard tools, which I think are on. You should be able to grab a sunburst just to the left of the map and then pin it to where you are. So I'm in Fort Collins, Colorado, which is about an hour north of Denver, and it looks like we're all from the United States here today. So from various places around the country, and that's great. It's neat to be able to do this without having to travel and spend any money. So I had a couple of polls on the next slide, but since there's just a few of us in the live meeting, I'll probably skip the polls and just ask you to put the answers in the chat box. So this is my email address and my Twitter handle. I really look forward to continuing the dialogue with you guys. So if you want to reach out to keep the discussion going, send me an email. That's my school email account, or drop me a line on Twitter. I check my Twitter feed pretty often, and I love getting tweets. So send me a message when you can. I teach at Preston Middle School. So we're a public school that has branded ourselves as a STEM school. It's a fantastic way to run a public school. It's much more about a philosophy than it is about the technology in the building. The philosophy being that of having engaged, creative, purposeful learners in the building, and really creating the learning experience in the building for one of that students can do inquiry and problem solving and learn to be critical thinkers and problem solvers. I'm just kind of curious about the background of the people in here. Do you have some experience with programming? Have you had just a little? Are you pretty confident with it, or is this something that's very new to you? I can turn on the polling tool, or you can just answer in the chat box. What's your experience with computer programming up to this point? Let me see if I can do the poll. Okay, and that's fine. Just answer in the chat box. Okay. That sounds good. I think that jives with what I see from most school teachers nowadays. The good news is that programming environments are getting easier and easier to learn. Back when we learned in the 1980s and 1990s, you would get cryptic error messages. Programs just wouldn't run. It was a really confusing and frustrating and difficult process just to get through the frustration of typing in all the code and getting it to work. It is so much easier now, and it's just there's almost no excuses not to learn it with the quality of tools we have these days. And I'm curious what you're hoping to learn from the presentation. I'll turn on the whiteboard tools, which I think they're on. Yeah, the punch cards are a common story. I've heard from a few colleagues that have used the punch cards. What would you like to get out of this? I'll tailor the presentation as best as I can to your needs. Okay, that sounds great. I'll try to answer these as we go through the presentation, and if you have other questions, be sure to raise your hand and let me know. My slide deck is online. I'll take this link and paste it into the chat box there. I've got a tiny URL. My blog also has kind of a repository of lessons that involve coding. I've organized them a little bit by unit and included links to rubrics and things like that. So that's the second link. The first link is just to this slide deck, and it has the active hyperlinks. So I'll type that in the chat box. And if you'd like to go there and follow along with the slides as I go through it, when we get to a link that we'd like to follow, you can just click on it in your browser and it'll take you straight to the link. A lot of them use Java and are kind of interactive, and they don't show up well in the web tour that shows up in Blackboard Collaborate here. Okay, so this is a little background about me. I do have a bachelor's in computer engineering. I graduated from Case Western Reserve University back in the 1990s, and I had a career as a software engineer at HP and Agilent for 9 years. So that I had some really early experience with coding, which was such a gift. When I was in elementary school and middle school, my mother was a technology enthusiast, and she got us our Atari 800 XL computer. And that picture you see in the lower right is me with the Atari computer at my 8th grade science fair. So she liked to get magazines that had computer programs in them. We would type in the computer programs and we'd see what we'd do, and we'd kind of hack them a little bit and change the programs. She would also go to what were then called BBS, Bulletin Board Services. It was sort of the precursor to an FTP or a website. We'd go there, we'd download programs, we'd hack them again and mess with them and try and get them to work. And that when I was in 7th grade, my little gifted and talented project for school was to write a computer program that could play a trivia game. I wasn't an amazing programmer. I programmed very simple things. I learned Atari Basic. I did very little with it once I got out of middle school. But what I reflect on later on in my life, after I got my degree and I became an engineer for a while, was how important and how formative those early experiences with coding really were. Because I had those positive experiences with coding early on in my life, I knew how to think like a computer thinks. I knew how to write algorithms like a computer writes algorithms. When I went to college with some people who were just light years ahead of me when it came to technology use. I went to college with people who had already started their own business in writing software. But I can hang with them. And part of it was because I understood how a computer thought, and I had some experience with this, and so I wasn't a complete newcomer. As I think back on that experience that I had with the mentoring and the early exposure to coding, it also jives with what the National Center for Women in Information Technology have found in their research, that in order to close the access gap for women and minorities in technology, that early exposure is one of the keys. And so I'm a really big believer in giving kids exposure to not just the use of technology, but creation with technology. I also believe that computer science is how we model math in the modern age. In the 1960s, when we sent people to the moon, we did that with slide rules and pencil and paper. Nowadays, the space program is all about using computers, and everything we do with math to model with it is using computers. If you're the treasurer of the PTO, you model with computers. It's just how we do math. It's been a little bit baffling to me as I've gotten more and more into it, how much we continue to rely on paper and pencil when it's just not how we're going to interact with math in our future lives. I also think about how I don't have any data to back this up, but here's my thinking on the gap in computer science later on in high school and in college. The gap for women and minorities well, for women especially, not so much for minorities, but the gap for women in fields like medicine and natural science is really close to closing. That's almost more women than men in some disciplines. But in computer science and the physical sciences, you just don't see as many women taking those classes. And I wonder if part of that isn't because if you want to study computer science, you need to seek out those opportunities nowadays. They don't just come to you. But everybody has to take math. Everybody has to take biology. Everybody has to take the natural sciences. I wonder if we didn't bring computer science to more students and get them involved and immersed in it early on and not force them to have to be the ones to take the initiative, if we wouldn't see more women and minorities taking these classes later. I also think that we need to do a better job at emphasizing the creative parts of it, the fun parts of it. It's social. We tend to view computer science as a very isolating discipline where you sit in front of a computer and you just do your work and you crank it out and it makes something run and it's very much by yourself. But in the real world, it's not like that. It's a very social activity and it's a very artistic activity, and it's extremely rewarding. And so we could change a lot about the way we teach computer science in schools. I also want to think about the consumer and the creator paradigm in schools, and this is something I think is really emphasized by this conference on educational technology in the classroom. Consumers will use tools created by someone else. They'll answer someone else's questions and they'll practice skills only deemed necessary by the teacher. If you are pushing out to students what they're going to consume with technology, everybody will generally follow the same path for learning, maybe at different paces, but you can pretty much predict where they're going to end up, and there's a fixed goal. With a creation view in a core classroom, it's a little messier and you have to be kind of comfortable with the mess. Students are going to create something totally new and they won't always be asking the same questions. So one thing I've had to get comfortable with bringing something like computer science into the classroom is that I may have a goal in mind of what it is that I'm trying to teach, and it's not always what all of the kids are going to learn. That the students are going to learn and own skills that they need in order to create a solution. They're going to all have a unique path for their learning, and as long as they're growing to some extent, we need to be okay with that. So there's tools that we need to use in the classroom to make sure they're learning the same things, but we can also structure some things to make sure that students are all learning something from their experience, and it's something new and unique to them that they completely own. Authentic learning is something that the administrators in our building have been pushing us to try and involve more and more in the classroom. Authentic learning is when you pick up content as needed in order to create an original product. You know it's authentic when you're sharing what you're learning, and what you're sharing is something that you own and that you've created. What is fascinating is how difficult it is to include authentic learning in math. And we've talked about this a lot as a department and have a hard time wrapping our minds around why it's so hard. Math is incredibly useful in society. We use math all the time, and yet it seems like it's really difficult to create a meaningful project-based experience in the math classroom. And we do it once in a while for one unit or another unit, but we don't tend to include it as a core part of the learning experience for mathematics. And it's interesting, and I don't have any real answers for it, but I think we need to make an effort to make our learning more authentic. And Maureen, I see your question there about Dan Meyer math problems. Oh gosh, I've read some of Dan Meyer's work. And I know he's very much into open-ended problems with a lot of questioning involved in them. And I'm trying to think about how much of that I would classify as authentic, where I would picture an authentic project is if you're doing a unit on surface area and volume, you're actually creating a 3D object, and you're using the math to solve some problems actually on a real-life contextual situation involving the surface area and the volume of that object. Maybe you have to design a swimming pool or design a 6-pack of soda cans, and you need the math in order to make your project come to life. So that's what I would consider an authentic learning experience. Computer science is one way that I bring authentic learning into my classroom. In mathematics, a lot of the concepts that I've focused on working on with computer science are a really good fit for modeling with the computer. Variables, expressions, and inequalities jump out as a really big concept that can be aided by working on computer modeling. You can learn about number theory and number sense, coordinate geometry, doing simulations such as on genetics, statistical studies, probability, things like that, general problem solving and creativity. One item I noticed in this slide is algorithmic thinking, and I saw somebody mentioned this a little bit earlier about how to get students to break a problem down and analyze it. Yeah, think logically and understand how to organize. That to me is at the heart of the algorithmic thinking. Taking a big problem and breaking it down into the smaller problems that you need to solve in order to make that happen. It's the most difficult part of including computer science in the classroom, but it has such huge rewards for the kids. And when they finally created their own algorithm for solving a problem and they brought it to life through the technology, they feel amazing, and it's a huge accomplishment for them. So I really consider that the biggest bang for the buck out of including computer programming in the class. If you haven't seen the standards for math practice, so again, I want to redirect you to the slide deck, and that's on that tiny URL I pasted before. That link. If you scroll down to this slide and click on that link for the standards for math practice, it takes you to the mathematical content standards that are sort of our process standards. I bring them up because most core disciplines have their content and their process standards. And if you look at the process standards with a lens toward modeling and technology, you can see that there's really a lot of overlap between what is just general good mathematical thinking and what's good mathematical thinking with tech. I'm curious about this roadmap to balance chemistry equations, and I wonder if you're talking about an algorithm for doing things like stoichiometry. So you'll have to explain that a little bit more to me. That's an interesting question. So somebody mentioned where should I start, and I think I heard some thoughts on how do I learn a new language. Before you choose a platform, those of us who are in computer science love talking about computer languages and platforms. Some of us are really evangelists for Scratch or for Python or for Hopscotch or Touch Develop. And there's so many languages out there that you can choose from. It can really make your head spin. There's so many more I haven't even mentioned. And you can get caught up a long time just trying to choose the tool. The tool isn't the most important part of the computer science, and what really should be the biggest consideration is what's important to you, where do you want to get your students to go, and you need to take a look at what technology you have to work with. If it's a set of tablets, a set of netbooks, a set of desktop computers, if you're checking out a lab once a week or something like that, you need to choose a platform that's going to work with your goals and your environment. But really the key is understanding what are your main goals for introducing programming in the classroom. For me, my main goals were to help the kids become better mathematical modelers. So I looked at every tool that I investigated through that lens. How do I get this kid to explore the mathematics by using this tool? So there were some that I ruled out because they weren't fantastic for mathematical modeling. There are some that you might choose to look at because they match your goals, your learning goals a little bit better. So I think the most important thing before you even choose a platform is just to figure out what's important for your classroom as far as your learning goals for your students. What are those overall objectives? Scratch, somebody mentioned, is a fantastic tool. I adore Scratch, and I'll be teaching a computer class next year with the 6th graders that uses Scratch exclusively. It's all online and it's web-based. That's very kid-friendly. The sign-on is you can keep the kids' identities anonymous, and that's wonderful. It's very social where kids can share and remix programs. It's graphical, it's drag and drop. One thing that some of my math teacher friends really enjoy is that the coordinate system in Scratch is right side up, meaning the x-axis goes positive left to right and the y-axis goes positive in the up direction. Not all computer languages are like that, and so if you kind of like for all your coordinate systems to be going the same way, Scratch is a nice tool. What I found difficult about it, and the reason why I ruled it out in my classroom, is that the screens are so small and on my netbooks that I have in my classroom that if once you started writing a longer program, you just couldn't physically see it all. I also didn't enjoy as much that you can't write your own functions, your little modular functions, and that was a math concept that I really wanted to hit on during the year, and I couldn't find any way around it in Scratch. One kind of interesting effect that I've seen with Scratch before, and it may show up differently in your classroom, is something that I read about called the keychain effect. In a book called Invent to Learn by Sylvia, I think you pronounce her last name, Libo Martinez, she talks about how when students get involved in this creation process and making something, sometimes they get so excited about the process of creating that they sort of cease to challenge themselves intellectually anymore. And in some in some situations when I've been working with Scratch, I saw that. The kids would make an animation, and they'd make the cat move around the screen and bounce in different directions and dance to music, and it was really exciting. And then they failed to take themselves further. They didn't learn about variables. They didn't learn about other events. They didn't learn about the coordinate system. And because they were kind of content doing those little fun interactive things in Scratch, and they didn't need them. So I decided against Scratch because I felt like a lot of the things that a kid wanted to do, they almost didn't need to learn math to do it. And I wanted the focus in my classroom to be on learning the math. So that said, yeah, I think that I appreciate the comment from Maureen, because I think if you've got structures in your place to make sure that your learning in that topic continues to progress, then you can make really good use of just about any tool. So I will play around with it next year, and I'm intrigued by Scratch and want to keep coming back to it. The tool I ended up using is Khan Academy's online version of JavaScript. It's not one I see talked about a lot in computer science circles, but I love it. If you may know of Khan Academy as just having their online videos and their math exercises and things like that. They also have a fantastic computer science platform. And I'm going to paste the link to it here, and if you want to open it up in a Chrome browser or something, you can play around with it and see what it looks like. So that's the link to their computer science program. You do khanacademy.org/cs. When you go there, you'll see a little intro to JavaScript, and you can choose to learn to program, you can create a new program, or you can browse other people's program. And their learn to program is really cool. You watch the videos, just like the Khan Academy mode is. You can go to little programming challenges, and when you complete the challenges, you get badges and points for doing that. Every challenge progresses fairly logically on top of the other challenge. The program compiles and runs real time right in front of you, so it's really exciting to do, and it gives you some pretty instant feedback. What I liked about it for my purposes is that the class management was really easy. My students already have Google Drive logins, and so it had this seamless integration with Google Drive. I liked the text-based language, even though I know they're kind of head-spinning for people who are new to programming. They're really good for modeling math expressions. The graphical languages had this way of modeling math expressions. If you wanted to do the quadratic formula, it would take several pages of dragging and clicking, whereas in Khan Academy, you could just type it out as a formula, almost like you would on paper. I like the lessons and tutorials. They make sub-planning kind of easy. So if I've got a substitute teacher in the room, I can tell the kids to do one of their lessons or their tutorials, and then give me feedback on what they did. There's a few drawbacks to it, and one of the biggest ones is that a text-based language can be a really high frustration exercise. You do have to be careful of your spelling and your capitalization and your punctuation. You have to be extremely precise with it, or else your program will not run. And that can be really challenging for students that have difficulty with writing anyway. So it's something to think about. I think for younger kids, I wouldn't find it as appropriate, but for the students that I teach in the 12 to 13-year-old range, it's working out quite well. So yeah, I haven't looked at Alice with Java in the background. I will have to make a note to give it a try. So there's so many tools out there. It is kind of head swimming. These are some other tools that I've seen people use in classrooms. One of my friends swears by Hopscotch just as a tool for teaching kids to think algorithmically. I've heard some people talk a lot about Touch Develop, especially if you've got iPads. This Code by Math website, I think I'll put that link in there too. It's kind of an interesting site. They don't seem to use any standard language. It's sort of a pseudocode that they developed. But what I like about the codebymath.com website is that they structure everything by math topic. So you can look up something like the Pythagorean theorem, and they've got some coding lessons on the Pythagorean theorem right there. You can look up linear functions, and there's some coding exercises on linear functions. You can look up percent, tax, and tip, and there's coding lessons on percent, tax, and tip. So even though I don't use the language in my classroom, I use the lessons that I find there for inspiration and to give me some ideas about ways I can use computer programming as part of math. Codecademy is sort of the gold standard of a site that you want to learn programming on. I would recommend checking it out if you want to learn a text-based language like JavaScript or Python. And then GeoGebra, which a lot of math teachers like, has its very own scripting language that some math teacher friends I know have gotten really into and have gotten pretty proficient at. Again, the platform's just a tool. You have to consider what kind of thinking and problem solving you want to develop around your content area and pick the tool that best fits that. Are you having kids do storytelling? Are you having them learn how to model expressions and equations? Whatever your goals are, that should steer you toward the tool. It'll jump out at you when you really have a clear picture of what it is that you want to accomplish. So that's kind of my spiel on tool selection, why we do computer programming in the classroom, and what you want to get out of it. The next few slides I have are on different ways to structure activities. I kind of want to pause for just a second to see if you have any questions on platform choice or the goals of including coding in the classroom. And then if you don't have any questions on that, I will move on to activities so you can see the different kinds of ways that I've incorporated it. That's a great question, Becky, and I didn't answer it yet. So for next year, I'm going to be teaching some 6th grade students for about half a day, and I'll have them for an 80-minute block every other day. When I do coding in the core classroom, usually what I set aside is about half a class a couple days a week. Since we're on a block schedule, I find that it's tough to keep the kids engaged in a coding exercise for an entire class block. So usually what we do is we break it up into halves, and one half of the class will be very traditional math instruction, and then the other half of the class we do some coding activities. I find that I can still keep pace with my colleagues. I'm covering just as much material, but it has started to feel right to do about half a class about 2 or 3 days a week. When I'm going to be teaching computer programming full-time, then I'll have every student for one block period, an 80 to 89-minute block period every other day. So I hope that answers your question. Let me go on to activities. So the first kind of activity that I include is an activity I call Wreck-It Ralph. The premise is something like this. I have a computer program. It works beautifully. Wreck-It Ralph got into my computer program, made some changes. It doesn't work anymore. And so the kids have to go into the computer program, and they have to fix my problem and see what's wrong with it. I do these activities when I've been teaching a concept for a little while, and I notice that there's some common misconceptions that are coming up, and so I want to address those misconceptions by bringing them to the forefront for the students and showing them in a way that gives them instant feedback on what that misconception is. So like example of one of them is this one that's the averaging problem. I'm going to grab the link to it, and I'll paste it in the chat box, so if you want to explore it, you can. This is a Wreck-It Ralph activity I did on order of operations. So I'm grabbing the link. What I noticed was that no matter how often we studied order of operations and practiced with it and worked with it, that nagging misconception about working left to right in a math problem still persists in some areas. And sometimes it's gone for a while and then it comes back, where the kids continue to want to both work left to right and then write math expressions with the math going left to right without any parentheses, just as if you were reading a book. So I wrote the averaging problem to bring that to the forefront of what's really happening when you don't include your parentheses and you're doing math from left to right. If you're clicking on the link, then what you see in front of you, I can't do the web tour. What you see in front of you is that there's a screen with 4 bars, and the bars are varying lengths, and I've got a number next to each one. Those numbers represent the numbers of students that attended pep rallies. The bottom bar, that 5th one, is supposed to represent the average of the attendance at all 4 pep rallies. So I asked the students to troubleshoot it and try to figure out what's wrong with it and fix it. This is a pretty early coding activity, so they don't have a lot of experience with it. So some of it is just pattern finding and problem solving, and they don't have to actually write any syntax. It's also great for kind of familiarizing them with the environment without having to actually write any code. And it's good for, it's a very low floor activity. Kids who have very little experience in math or coding can access it, and they can work with it, and they can feel successful at it. So if you see the problem with it, I'm kind of curious if any of you guys noticed what was wrong with the program. Yeah, you see it? Yep, it's that lack of parentheses in the statements. So the kids realized then that working left to right was the problem there. The problem was only dividing the fourth number by 4, and then it was just adding everything else. They check it with their calculators, and they see that that was the problem, and then they fix it, and then they feel really accomplished because everything just looks correct then. For kids that finish early, it's nice to have an extension activity. So I'll add a challenge prompt to the bottom of all my Wreck-It Ralph activities, and the kids who have finished early and are kind of high flyers and want to do more with it, they can take on the challenge prompt and go a little bit further. So on this one, I challenge the kids to try and find the if statement and then pop up a message showing whether you're meeting your quota at your PEP assemblies or not meeting your quota. If you scroll down the page, you can see some of the programs that my students have spun off. So some of them solved it and saved their spin-off. Some of them didn't save their solution. You know, it's fine. It's fun to get them to work in groups and talk about the solutions together. So those are Wreck-It Ralph activities. On the slide deck that's online, I've got links to these other ones too that address different math concepts. When I noticed that students, when they were calculating volumes of 3D shapes involving circles in the bottom, they always found the area of that shape by doing pi times radius squared. They think pi times diameter is both circumference and area. And so I brought that out with that % error of volume activity. Inequalities was something I brought up in a couple of different Wreck-It Ralph activities. Proportional relationships was brought out in that population graph, and then translations and congruence transformations. So just different activities that I brought out when I noticed that kids were struggling with the concept and had some misconceptions out there, just to expose them and bring them to the forefront. Next kind of activity I do is a starter program. So I'll use this when we've started working with the math of a concept, but we haven't gotten too far with it. And I want the kids to be able to do richer problem solving, maybe more difficult problem solving, maybe problem solving where they get some instant feedback on whether the model is correct or not correct. And maybe I also kind of want them to learn how to do the model with technology. It's time for them to pick up how to do some programming, but with scaffolding. And this fractions and ratios starter on this page isn't the best one that I have. A better one is this enrichment with percents. So I'm going to copy it and I'm going to paste it. This was a kind of a long activity that we did as an enrichment for students when we were learning about multi-step percent problems. So the premise behind it is that you are a sod salesman, and people are going to give you the dimensions of their yard, and you have to calculate how much it's going to cost to put sod in the yard. So the students by this time had worked with percents, they'd worked with area, they'd worked with rates. They hadn't really synthesized all of them at once into one common activity. And so to do that, we brought in the computer model. The kids work with this program, and I give them the width and the height of several yards and a little word problem about that yard, and then they have to put the math in the computer program that's going to calculate the price of the sod. So they had a lot of fun with this. We had them work in groups. It took a whole class period for this one. We did take almost the full 80-minute block just working on this one set of problems. But the kids loved it, and for some kids it was their first experience computer programming, and they really did pick up on it pretty quick when they worked in groups to problem solve through it. So I'll give you a couple of seconds to explore those things. Again, the starter programs are they're useful for just exploring a concept kind of in depth. I did the feeding reptiles program when we were starting to work on connecting rate problems with equation problems. In the Common Core, this different representation of rates really shows up as a big goal. So I wanted students to start experiencing modeling rates with equations, and the best way that we could do that so that they would really know if they were right or not was to put it in the computer program. And then to start our work on inequalities, I taught the students how to do button clicks by giving that % button starter at the bottom. So they could learn how to find a region on the screen by knowing whether the x coordinate was greater than something or the y coordinate was greater than something. And when they could model that region of the screen as a set of inequalities, then they would use that as their if statement to make the button work. And I guess I'll just say lastly, one really interesting thing that came up with the enrichment with percents was there's one problem in there. I think if you scroll down the page just a little bit, yeah, there's a problem in there that talks about a yard that has 10% more area than you thought. That was a really fascinating activity to work through with the kids because they had a hard time wrapping their minds around whether you increase just the width by 10%, just the height by 10%, or both. So it was I wondered if I shouldn't have structured that problem a little bit differently, because a yard that's 10% bigger in both dimensions doesn't look a lot different than a yard that's bigger just in one dimension, but they only needed to increase one dimension by 10%. If you increase both dimensions by 10%, the yard actually ends up too big. You really notice it if you increase it by like 50% or 60%. You can tell the yard ends up way too big for what you intended. But when you increase it just by 10%, you don't see it as much visually, but the math ends up wrong. So, and she says, do you have kids that have trouble with the syntax but could do the math, or do they get over it and having the program just gives them other ways? Yes. And I would say more often the kids that have trouble with the syntax also have trouble with the math. So it's not as common for a kid to just have the problem with the programming language and then less problem with the math. So it's been interesting to see how the two go hand in hand sometimes. And I do notice there are some kids that have a lot of trouble with the math that seem like they kind of do better with it in a programming situation, where if I work with them on pencil and paper, I can barely understand what it is that they're doing, and they have a really difficult time communicating their work and a really difficult time problem solving through it. But when it's right there in a computer program, they even articulate what it is that they're doing better. They explain it better. So I guess it's kind of made me a believer in kids have some different strengths, and it's really helpful to have those different modalities of looking at a problem, where some kids are going to really thrive on the pencil and paper, but not everyone will. And so if we have those different models for them to show what they know, it's helpful for drawing the knowledge out of some kids. Yeah. Another kind of activity that I do is just a direct or a flipped lesson. So a direct lesson is when I'm in front of the classroom just showing the kids how to do something on the computer. I do this less often than you'd think. A lot of times I have them work through a problem-solving activity with, where I'm not teaching, I'm just kind of facilitating. But when I do need to teach them something, they're not going to learn about if statements and while statements all by themselves. They do on some level need to be taught. And so I'll teach the kids in front of the classroom, and I'll also make a video. So, and I've started to get to the point where I give them the choice. You can work through the lesson with me in the front of the classroom, or you can take your computer in the back of the classroom with your earbuds, watch the video, and do it at your own pace. Some kids find that the class moves too slowly or too quickly for them, and it's helpful for them to have the video. And some kids like having the explanation as we go through the lesson, and so they like to sit through it with me. It seems like less students prefer the video, more students like to go through the lesson with me, but there are some kids that really like using the video. So these are some lessons that I've done as flipped, and for the most part, they're for introducing a new programming technique. I introduced the if statement with the video, arrays, and then using loops. I think where I came to this was that if a student could use if statements, loops, and variables and expressions, they would really be able to do just about any math modeling that I threw at them at the stage of learning that we're at. And so they were really small programming goals. We didn't have to become rocket scientists at it, just making decisions and going through looping. And those things are on the slide deck online if you want to click on those. I don't have very good video capture software. I'm kind of working on it. So they're just more of examples of how I use the videos to get across a new concept in programming. And then the last kind of activity that I'll use is the unit project. So this is the big summative authentic assessment at the end of a unit. I've done 3 of these so far in the classroom, and I love this. This is, these days when we work on the projects are the days that I live for in the math classroom. So when I have the students do a unit project, they have to produce a computer program, they have to write about it, and then they have to share their product with me. When I grade them, since I'm a math teacher, my rubric really has to be focused on just the mathematical assessment. So I only grade them on a scale of 4, 3, 2, 1 on how well they did and communicated the math. But they do have to produce a technology product. And I talk to them about how when I'm an engineer and I'm working with my coworkers, if I write a computer program, part of my product that I have to deliver to my coworkers is a little design document that explains what my program does and how it works. And so they always have to write me at least a paragraph telling me what their program does, how it works, and how they modeled the math that they were supposed to model. So that has to be part of the product, and I'm really a big believer in including that writing piece because it kind of helps them to own their own thinking. So here is the first unit project that I did with my kids, and it was on congruence transformations. I can grab that link and I can paste it into the chat window, so let me grab that if you would like to see it on the blog. On the blog, what that looks like is just the sort of sequence of lessons and then the rubric that I use to grade them on congruence transformations. Since my standards, hold on, let me paste the link in there. Since my standards said that students had to be able to identify, verify, and I think the words were, was it identify, verify, and create congruence transformations of rotations, translations, and reflections. That was basically what I was assessing them on. I needed them to be able to identify them. I needed to tell me the properties of the congruence transformations, and I needed them to be able to tell me how they worked. If they could also explain the coordinate rules that they used to make the transformations, I kind of considered that advanced, and I would give them a 4 on the rubric. So it was a wide open project. Create some artwork that shows congruence transformations. You can use any combination of translations, reflections, and rotations. Explain to me how you know that they are the transformations that you used, and to go for the advanced, and then explain to me the rules. We did not do tessellations, although that's a really interesting use of the translations, is including a tessellation project. So I will show you some of the projects that they did. They are really cool. I was really skeptical that this was even going to work when I started the project, and it took a long time for the students to get going, and getting used to the syntax of programming was extremely tough. There were some times when I wasn't sure that we were going to get there. And then all of a sudden I looked around, and these kids had this beautiful artwork on their computers, and they were really excited about it. And they shared it with each other, and they wanted to come and show me what they made, and their parents were emailing me, and they were all excited about what their kids had made. And you can see some of these pieces of artwork are kind of complicated and really involve some kind of tough math. So they went above and beyond what they were supposed to do because they wanted to make it look beautiful and interesting and creative. And I was really impressed with the work that they came up with. So those were their projects on congruence transformations. And again, the product was only part of this. They had to write me a good explanation of how they knew that those congruence transformations worked. I rotated this 90 degrees, and this is how I know it's rotated 90 degrees. I reflected this across the y-axis, and this is how I know it's reflected. So yeah, I've never programmed a tessellation before, but I can imagine how it would be done. And I think it would be easier if you had the concept of looping, which we didn't have at this point in the year. So I think that's kind of why I shied away from it, was we didn't have that algorithmic learning yet. So the next project that we worked on was a project on rates and ratios. And I've thought hard about how to include a technology project into this concept. And what occurred to me was that when you create a data visualization like a graph, you're really doing a lot of proportional reasoning. you have to reason out what's the scale of the screen that you're working through. You have to reason out what's the size of the data that you're working with, and you have to find a way to scale your data so that it fits in this space and everything is still proportional to each other. So I challenged the kids to create a graph or a visual model of some kind of real-life data that they collected. It could be survey data they found online. It could be a survey that they did in class. It could be some data that they found on, say, Yahoo Sports, but some kind of visualization that showed they understood the proportionality of that data. And then I wrote the rubric, and the rubric, again, really judges the kids on creating a visual model of their rates, ratios, or fractions, displaying it in a unique way creatively, and then explaining their data and how they made their model. And so then I'll show you some of the projects that they made with ratio and proportion. And they were, they were amazing. The math behind creating a pie chart is a lot more difficult on a computer than you would think at first. The kids have to, they know that there's 360 degrees in a circle, but they don't really consider how to scale that 360 degrees so that it takes up a proportion of the chunk that's proportional to their data. So they had to work through some pretty tough math to get those charts to show up like they were going to. They had to use variables and expressions, and so it involved modeling their proportionality using equations, which is also part of the Common Core standards. And they did some awesome work. There's one picture on this slide that has a little bar graph in gray, and it says, what makes more money, a photographer or a cook? And that bar graph that's up there is so cool to me, and it makes me smile because the kid who made this is an 8th grader who's taking 7th grade math a year late. So he's a year behind where he should be. And I knew that he was challenged by learning math, and watching him work through this project was just fascinating. He really wanted to know if he should pursue being a chef or if he should pursue being a photographer as a career. So he used the internet to figure out who makes a better salary and then display a graph of their salaries on the screen. And I don't think the information is exactly 100% correct, but he worked so hard at trying to work out the math so that he could make a convincing graph of his future careers. And it was just he was a fascinating kid to work with. So I think he was really proud of his project, and he's done some great work programming since then. I'll tell you about the last unit project that I did, and then I'll open it for a few more questions. So the last unit project that I did was on expressions and inequalities. At this time, most of the stuff that we had done in class was really simple programming. We had done drawing shapes, writing variables and expressions, and sometimes it would be like an if statement here and there. This one added on a whole new dimension of the programming where the kids actually had to think through a sequence of events that would make it a game. So the kids really wanted to make video games, and this was in March, I guess, that we decided to go ahead and pursue this. And we said, all right, we'll go ahead and do a video game as a project. So I challenged the kids to make a little mini game like the kind that would show up on The Price is Right. I thought it would be a pretty good model of expressions and inequalities, because on The Price is Right, you have to have the price be either above or below a certain range in order to win. And most of the challenges that we had with this were really surprisingly not related to the math at all. It had nothing to do with trying to calculate the price of the objects that they were buying. It really had to do with that problem solving of breaking down. I've got this vision of a game. I kind of know what I want it to do. How do I get my program to do that? And that part of the teaching was really tough. And I'm really proud of my kids for working through that, but it took a lot more time than I thought it was going to. And I would love to share with you some of the games that they made. They're pretty cool. So I'll copy the link to their games in here. Let me copy that, and I'll paste it in the chat window. Okay, and again, this is linked to the slide presentation that's on that tiny URL as well. This game board has, I think you might need to view the slideshow to see the links to the games that the kids made. They had to use an expression with variables that would tell you whether somebody won or lost, and they had to use inequalities to tell you whether somebody won or lost. And I felt that it matched the 7th grade Common Core standards on inequalities fairly well. But again, the math part was not the hardest part of this. The hardest part of this was trying to figure out, if I want the people to be able to select like 3 different items, total up their prices, and figure out if it's between $20 and $25. How do I do that? So the algorithmic thinking was very tough, and I keep thinking back to myself, how do we develop that skill in kids? How are we purposeful about developing that that algorithmic and computational thinking? It feels like it's an important part of a kid's math learning, and knowing how it develops naturally and what kind of experiences develop it in kids are not something that I found a lot of resources on. So yeah, I'm with you, Maureen. I think a lot of times a kid's vision of what they want to do is really complicated. And once they start storyboarding it out and realizing how complicated it is, they realize they need to scale it back. And I sort of processed to myself, could I use storyboarding or flowcharting types of techniques to help the kids develop that problem solving on their own and not need so much support with the algorithms? So yeah, way back. It's fascinating. The finishing to this project, though, once the kids worked through their problems, and they worked hard. They stayed after school. They worked, well into the next passing period. They really wanted to get their games done and make them work well. And I gave a little survey when the project was done just to find out their perceptions of it. And I thought the survey results were really encouraging. Most kids thought it was fun. Very few kids thought it was boring. Very few kids thought it was easy. Most kids thought that it was a tough project, but an enjoyable project, and they found it really rewarding. I think it was a good way for them to learn the math of expressions and inequalities in a little different way than paper and pencil. I don't know if any of you had concerns about introducing programming in a core class and what it does to student growth. I wanted to bring up this slide because I don't have a ton of data on student growth, but the little that I do have is encouraging. Last year I included some computer programming in class, not as much as this year, and I don't have this year's data yet. I am kind of a nerd about analyzing my data, so I wanted to see how my students were growing doing some programming last year. It didn't change much. The growth was still on par with the rest of the school. The students still made a year's growth or more. I think I was kind of hoping to see a big difference from years before, but I guess I found it encouraging that I did no harm, that I still got through the math content that I needed, and the kids were engaged in problem solving with computation. They learned some new things about computer science, and they had some positive exposure to STEM while still maintaining their growth in math. It is also hard to isolate coding from other changes that we make, and so that's something I need to reflect on as well. Yeah, I'm with you, Maureen. I kind of convinced myself that if we are teaching the kids how to think, how much attention do we pay to the test scores? So I think that the test scores should be part of the conversation, but what kind of learning experience are we giving to the kids is the bigger part of it. The student reactions to this have been really awesome. And so I put in these quotes of some things students have said about programming as we've gone through this. The one that sticks out to me the most is when we did our unit, I taught the kids how to do reflections. I did worksheets with them on reflections. We took a quiz on reflections. And then I gave them a computer programming project on reflecting shapes over the Y and the X axis. And when we did the computer programming projects, the kids waved me over and they said, Mr. Priest, did you know that if you flip the sign of the X coordinate, it reflects? And I would say, I know, I taught you that. We took a quiz on it. We did a worksheet. Do you remember the quiz and the worksheet? And they would say, no. But did you know that if you flip the sign, it reflects over the Y axis? It's crazy how they didn't retain the information when it was taught to them, but they retained the information when they got to experience it on their own, when they created it. It was powerful for me because I had heard the saying before that if you involve me, I understand. And I think that was the first time I'd ever actually seen it in action, that they learned something better by creating it than by having me teach it to them. this is some food for thought. I'll give you a second to read that quote by Isaac Asimov. And I think this is the end of the presentation. I didn't leave as much time as I hoped for question and answer, but it's kind of a small group, and I would like to know what questions did you have that I didn't get to? I will turn on your microphones. If you'd like, you can talk by clicking the talk button under the little webcam video, or you can just type questions in the chat window if you have any. Well, thank you for your positive comments. It's been a fantastic experience. I will have to say I've really enjoyed bringing computer coding into the classroom. I love my job on those days when we come in and we're doing computer programming, when the kids are problem solving and they're making progress and they're tinkering and they're trying new things and they're running across the room to share with somebody what program they did, and they're adding each other as coaches and friends so that they can share programs with each other. And they're telling me that they stayed up late last night to work on a computer program. It's just so exciting. And it's neat to see them be so creative with something. And yeah, Maureen, I hear you on the benefits of learning a syntax in a language. I don't know, depending on the age of the student, that's a decision you need to weigh really carefully. I chose to have the students do a text-based language mostly because of the variables and expressions part of the math content, that the students had to learn to write algebraic expressions with variables in them. And in a text-based language, those expressions look like math expressions. The variables and the syntax and everything looks so much like math. So I chose a text-based language for that reason. If your purpose isn't to work on the algebra part of math, I wonder if a graphical language wouldn't be better suited for your needs. If it's more about problem solving and algorithmic thinking and that kind of computation, that maybe a tool like Scratch is a little better. So Becky, I appreciate your comments too. That's going to be my challenge next year. So I'll be teaching computer technology, and we'll be trying very hard to integrate core classes into it. Thank you all for coming. I very much appreciate your participation and for coming to the seminar. It's been a great conference. Thank you very much.